careful to do it. It's quite nice when it's done at the end. And you don't have to worry about it.
Hello. This algebra workout is about complex numbers. What we're going to do in this programme is show you how to do arithmetic with complex numbers.
But what are complex numbers? Well, complex numbers are actually very similar to real numbers, except that we include this extra symbol I. And I has the property that I squared equals -1. Now, there's no real number with that property, so I is definitely not a real number. We call it a square root of -1. You may find it hard to imagine this, and in fact, that's where the name imaginary comes from. I is imaginary.
In the first problem, we're given two complex numbers, z and w. And we're asked to add them, z plus w, multiply them, z multiplied by w, and then divide one by the other, z divided by w. The second problem looks a little bit more challenging. We're given a particular complex number, and we've been asked to evaluate the 10th power of it, in other words, to find that complex number to the power 10. So that's essentially multiplication. And finally, we're given a question where we have to solve an equation involving complex numbers. So the answer will probably be a complex number. To start with, Alan's going to remind us about basic arithmetical operations on complex numbers.
Well, here's a couple of complex numbers. 12 minus 5i and 3 plus 4i. You can see that we've made them by taking real numbers and combining them with I in this way. And a general complex number is of the form a plus bi, where a and b are both real numbers. A is called the real part of the complex number, and b is called the imaginary part of the complex number. So paradoxically, the imaginary part is in fact a real number, the real number that multiplies I. Now, if you want to use a single letter to describe the complex number, we usually use the letter z or w. But z is the basic letter, just like x often is for real variables. Now, you can see that if b equals 0, then z equals a, so z will be a real number. Well, what we need to know is how to do basic arithmetic with complex numbers. And we actually do it more or less as if the complex number was a real number. But we have to keep remembering that I squared, whenever it appears, is equal to -1. So, for example, if we wanted to add the two numbers that are in Sarah's problem, 12 minus 5i and 3 plus 4i, then we would collect together like terms. So the 12 and the 3 would go together, and the -5i and the 4i would go together. And putting these together, you get the answer as a complex number. So, over to Sarah to add these two together.
Thank you, Alan. A nice bit of simple arithmetic. That makes a change. So, as Alan says, I'm going to add these two together. Z, that's 12 minus 5i, and W3 plus 4i. And I've written that out here. So I'll begin by collecting together the like terms. So I have 12 plus 3, and that's added to -5i plus 4i. Well, now it's simply a case of doing the arithmetic. So 12 plus 3, that gives me 15. And -5i plus 4i, well, that gives me -i. And that's 15 minus I. So there's my answer as a complex number.
Well, that seemed pretty straightforward. And honestly, multiplication's not any more difficult. If we want to multiply 12 minus 5i times 3 plus 4i, well, it's the usual method of multiplying out two brackets. You've got to multiply each expression in the second bracket by each expression in the first. 12 times 3 to start with, and then 12 times the 4i, and then the -5i, which we've not touched yet, -5i times the 3, and finally the -5i times the 4i. And that's where the I squared equals -1 comes in. Sarah?
Well, OK, Z times W, and I've written that out here. Well, 12 times 3 is 36, and 12 multiplied by 4i, that gives me 48i. -5i times 3, well, that's -15i, and -5i times 4i, that gives me -20i squared. And I need to remember that I squared is -1, so let's write that in. So that gives me 36 plus 48i minus 15i. minus 20 multiplied by negative 1. So now I just need to gather up the terms and combine the i's. So this end term here, minus 20 multiplied by negative 1, that gives me 20. So 36 plus 20, that's 56. And 48i minus 15i, well, that's 33i. So the result is 56 plus 33i.
And finally, here's the division problem that Sarah will have to do. We're going to divide 12 minus 5i by 3 plus 4i. Well, divisions are a bit more difficult, but there is a trick. And once you've got the idea, then it turns out, honestly, to be quite straightforward. Let's consider the 3 plus 4i separately. And let's see what happens when we multiply 3 plus 4i by 3 minus 4i. That's the same complex number, but with the centre sign changed from a plus to a minus. And let's see what that equals. Well, we've just done some multiplication. We want to multiply every term in the second bracket by the terms in the first. 3 times 3 giving us 9. Then 3 times the negative 4i, that will be negative 12i. So on the bottom here, we've got 9 minus 12i. Then the 4i times 3, giving us a plus 12i, which has to be added in. And finally, the 4i times the negative 4i, giving us a negative 16i squared. Now, remember, I squared is negative 1, so we have negative 16 times negative 1, which changes that last term to a plus 16. Now let's gather together the like terms. The negative 12i and the 12i cancel out, so the imaginary part is disappearing, and we're left with a real number, 9 plus 16, which equals 25. So the fascinating thing is that the product of these two numbers gives a real number, 25. Now, we actually have a symbol which links a complex number with the complex number you get by changing the sign in the middle. We write 3 plus 4i with a little bar on top, and that's equal to 3 minus 4i. And we call 3 minus 4i the complex conjugate of 3 plus 4i. Now, getting back to Sarah's problem, all Sarah needs to do here is multiply top and bottom by 3 minus 4i. That's the complex conjugate of 3 plus 4i, because multiplying top and bottom doesn't change the value of a fraction. So let's go back to Sarah to see how that trick actually works in practice.
Well, I've used the trick already. I've multiplied top and bottom by 3 minus 4i. That's the complex conjugate of 3 plus 4i. And as Alan showed you, we get 25 in the denominator. So that's very helpful because now we've got a real number in the denominator. So now I've just got to multiply out the top pair of brackets as before. So 12 multiplied by 3, 36. 12 times negative 4i minus 48i. And negative 5i multiplied by 3, that's minus 15i. And negative 5i multiplied by negative 4i, well, that gives me a plus 20i squared. And that's all over 25. So now I'm going to collect the terms together. And I need to remember that I squared is negative 1. So this end term will become negative 20, so 36 minus 20, that's 16. And negative 48i minus 15i, well, that's negative 63i all over 25. Now, I could leave it like that, but I think I'd like to put it back into an a and a bi form. So I'm just going to separate out this fraction into 16 over 25 minus 63 over 25i. So that's the last part of the first problem done. So let's look at the second problem. That's 1 plus I to the power 10. So that's really just a simple multiplication. I need to take 10 copies of the complex number 1 plus I and multiply them together, and so on. Well, I think you can see that that would be very tedious. In fact, there is an easier way to do that problem, which Alan's going to tell us about.
Well, in order to do that problem, we're going to talk about how to interpret complex numbers geometrically. We're going to have a geometric picture of what they are, and that is really useful when you're working with them. So this is called an Argand diagram, and it's similar to a Cartesian diagram. This horizontal axis is called the real axis, and the vertical axis is the imaginary axis. So let's put the complex number a plus bi onto this diagram. If this is a complex number a plus bi, then the distance here along the real axis is a, that's the real part of the number, and the distance up here parallel to the imaginary axis will be b. And the point AB now becomes our representation of the complex number a plus bi. Now, let's do a couple of examples. Let's put the complex number 1 plus I on here. Now that would be 1 along the real axis, and the I means it's 1 up the imaginary axis. So the complex number 1 plus I would be up here, at the point 1, 1. Complex number 1 plus I. Now how about the complex number, say, negative a half I? Well, it has no real part, so it's down here, actually on the imaginary axis, with a distance of a half from the origin. Negative a half I. Now, you could describe the addition of complex numbers using this diagram, and you would find that when you add them, they behave in a very similar way to vectors. But really, what we really need to do is to discuss a geometric interpretation of multiplication of complex numbers. And to do this, we need something called polar form. So, what's polar form? Well, let's take a typical complex number z, which has a real and imaginary part. And let's find the distance r from the origin. And let's also then measure round from the real axis and call this angle the angle theta. Now, theta is measured in radians round from the positive real axis and has a positive value if we're going anticlockwise. So if you know r and if you know theta, then that will tell you where the complex number is. The notation we use for representing this complex number is angle bracket with r and theta inside, and then we close the bracket. Now, r is called the modulus of the complex number, and theta the argument of the complex number. So this is a different way of representing complex numbers in terms of the distance and the angle. So let's now look at an example. Let's take the complex number 1 plus I. Now, 1 plus I was 1 along and 1 up, so there it is there, 1 plus I. So what distance is it from the origin? What will the modulus of 1 plus I be? Well, the distance up here gives us the modulus, and this distance is 1, the height is 1, so by Pythagoras, this modulus will be the square root of 2, root 2. Now we need the angle. This angle here, well, because that's 1 and 1 in a right angle triangle, it'll be 45 degrees, or in radians, pi by 4. So 1 plus I is represented in polar form by root 2 pi by 4.
So that root 2 pi by 4 represents my complex number. So 1 plus I in polar form is angle brackets root 2 pi by 4. Close angle brackets. Well, before I continue with finding the 10th power, let's look at one more example.
Well, let's take the number negative a half I, which will lie here on the imaginary axis, a distance of a half down from the origin. So the modulus of the complex number is a half. What about the argument? Well, the angle round here is 3 pi by 2, so the argument is 3 pi by 2. But we could have chosen our angle coming clockwise round here as a negative angle, negative pi by 2. And we have an alternative way of writing negative a half I in polar form as a half negative pi by 2. In fact, there's an infinite number of ways of choosing that angle. So, what angle do we choose? Well, what we usually do is choose the angle between negative pi and positive pi, and that is the principal value of the argument. So let's get back to our problem. The first step in this method of working out powers is to represent the complex number in polar form. Sarah.
Well, the complex number I've got here is 1 plus I, and we've just seen that we can represent that in polar form as root 2 pi by 4. So the next step is to deal with this 10th power by multiplying complex numbers in this polar form, in particular working with powers of complex numbers in polar form.
OK, well, if we have two complex numbers in polar form, there's a particularly simple way of multiplying them. It's simply multiply the moduli and add the arguments. And here's how it works. Here I have the complex number z, the first of our two complex numbers, and it has modulus r and argument theta. Now let's add w to the diagram. And let's give w a modulus of s, and the argument for w will be phi. So phi is the angle round from the positive direction of the real axis. So w is the complex number in polar form, s phi. Now let's see what happens when we multiply z with w. Well, first of all, the argument is going to increase. In fact, it increases by an amount theta. And the modulus of our zw is going to be r times s, the product of the moduli. So the complex number zw has as its modulus rs and as its argument the sum of the two arguments, theta plus phi. So zw in polar form is rs theta plus phi. So we multiply the moduli and add the arguments. So that's how we multiply complex numbers. But what we need to do for Sarah's problem is not multiply, but to raise to powers. We want z squared, z cubed, etc. So let's go back to our z in polar form as r theta. If we square z, we get r theta all squared. That would be r theta times r theta. Multiplying the moduli, r times r would give r squared. Adding the arguments, theta plus theta, would give 2 theta. So that z squared is actually equal to r squared 2 theta. Now, following on from this, if we wanted z cubed, that would be r theta all cubed, which would be r cubed 3 theta. And the general case for n, any natural number, z to the power n would be r theta to the power n, r to the n, n theta. And that's exactly what Sarah needs in order to do the problem.
Well, OK. 1 plus I to the power 10 will be root 2 pi by 4 to the power 10. And so to work this out, as Alan says, I need to raise my modulus to the power 10, so that's root 2 to the power 10. But I have to remember to multiply the angle or the argument, so that gives me 10 pi over 4. Now, can I simplify that any further? Well, let's have a look at the root 2 to the power 10. Now, according to the properties of powers, I can rewrite that as root 2 squared, all raised to the power 5. Oh, well, that does help me because root 2 squared is just 2. So 2 to the power 5, well, that's 2, 4, 8, 16, well, that's 32. So I can rewrite this as 32 and, well, 10 pi by 4, I can see straight away that that's 5 pi over 2. Now, can I simplify that 5 pi by 2 any further? Well, let's have a look at it on a simple diagram. 5 pi by 2 is just 4 pi by 2 plus another pi over 2. Well, 4 pi by 2, that's 2 pi, that gives me one complete cycle of 360 degrees. In other words, it brings me back to where I was before. So plus the pi by 2, that means that 5 pi by 2 gives me the same angle as pi by 2. So I can rewrite this as modulus 32 and pi by 2. So that's the answer in polar form, but we need to give the answer in the form in which it was asked. So what does that look like? Well, 32 from the origin, well, that gives me 32 along the imaginary axis. So I'll write that as 32i. And you could have found that by just multiplying the number out. But once you get the hang of polar form, you'll find that it is much quicker.
So now on to the final problem. And this looks a bit more tricky. We've got to solve an equation z to the power 10 equals 32i. Well, from the work Sarah's just done, we discovered that 1 plus I to the power 10 equals 32i. So we already know one solution, that z equals 1 plus I. But actually, there are 10 solutions altogether, so we're still to find another 9.
So just to recap, we know that 1 plus I to the power 10 equals 32i, and we're looking for z to the power 10 equals 32i. And we know that one solution, therefore, is z equals 1 plus I. So what we're going to do is look for solutions of the form z equals r theta. So we're going to search for a solution that's in polar form. So I'm going to need to express the original equation in polar form. So what's 32i going to be? Well, we saw in the solution that that was modulus 32 with an angle or an argument of pi by 2. Or it could be 32 and an angle of 5 pi by 2. Or it could be 5 pi plus 2 pi, or plus another 2 pi. In fact, it can be a whole sequence of different representations in polar form. In each case, you add 2 pi to the argument, and we'll come back to that in a minute. So my equation then is z to the power 10 equals r theta to the power 10. And how do I work out that? Well, as Alan said, I need to raise the modulus r to the power 10, but I've got to remember to multiply the angle or the argument, so that's 10 theta. And I know that that's equal to 32 pi by 2. Now we want to equate the moduli r to the 10 with 32. Well, what does that give? We saw in our earlier work that that means that r equals root 2. So lucky we did that earlier. Now let's equate 10 theta with pi by 2. But of course we know there are lots of different arguments on the right. We can add on any integer multiple of 2 pi, so let's call that 2 pi m in general. Now I'd like to find theta. So dividing both sides by 10, well, that gives me pi over 20 plus 2 over 10, so that's 1/5 pi m. So we have two equations and we've worked out from one what r is. And now we've got to work out from this equation what the values of theta can be. Well, at first sight, it looks as if there are infinitely many possible values of theta because there are infinitely many different values of m. So let's see what happens if we go through them, see if we can spot a pattern. So if we take m equal to 0, well, that gives me pi by 20 because this term on the right-hand side, 1/5 pi m, well, that just disappears. M equal to 1, well, that gives me pi by 20 plus, well, that's 1/5 pi, so pi over 5. And m equal 2, well, I get my pi over 20 term again, plus 2 pi over 5. And so on, I could carry on. Well, I think I'll just tidy up these fractions here to help me see if there is a pattern. So theta equals pi by 20. Finding a common denominator here, so let's use 20 on the bottom, multiplying this term by 4, that gives me 4 pi plus pi, so that's 5 pi over 20. And doing the same thing here, so 2 4s are 8, plus another pi, that gives me 9 pi over 20, and so on. And you can see the pattern there. They're all over 20, and on top you're increasing the multiple of pi by 4 each time. So we have a sequence of values of theta, and we know that r is root 2. So let's write down the solutions to the equation, and we'll call this first one z0. So z0 equals, well, I've got my modulus of root 2, and my first statement here, so that's pi over 20. What about z1? Well, when m equals 1, again, I've got my same modulus, that's root 2, and my second term here, so 5 pi by 20. And z2 in the same way would be root 2, and my third term, so that's 9 pi by 20. And so, for example, I could work out that z9 would be, well, I know my modulus is root 2, and if I follow the pattern each time I'm going up by 4, well, that'll be 37 pi over 20. I could have carried on, but I'll stop there and Alan will show you why in a minute. But you might be saying, well, I know that 1 plus I is a solution. Where is it in this list? Well, of course, I haven't expressed these in Cartesian form yet.
So here is our complex number z, written in polar form, r theta, where r is the modulus and theta is the argument. Now, in Cartesian form, it would be written as a plus bi. And we now want to find a and b in terms of r and theta. Well, a is the real part here, and by elementary trigonometry, the cosine of theta is a over r, so that a is r cos theta. And by a similar argument, b, this distance up here, the imaginary part of the number, while by similar trigonometry, b is r sine theta. So our complex number z, a plus bi, can in fact be written as r cos theta plus r sine theta I.
So what about my 1 plus I? Well, looking at line Z1, that's root 2 5 pi over 20, I can see straight away that that simplifies down to pi by 4. So Z1 is root 2 pi over 4. And I saw earlier that that is 1 plus I. So let's check it using Allen's formula. Well, if we know that Z equals root 2 cos pi by 4 plus root 2 sine pi by 4 I, cos pi by 4, well, that's 1 over root 2. So I can write this as root 2 multiplied by 1 over root 2. And sine pi by 4, well, that's 1 over root 2 as well. So this term becomes root 2 multiplied by 1 over root 2i. That does simplify down to 1 plus I. And that is the result I promised you before.
So finally, I'm going to show you the solutions that Sarah found on an Argand diagram. Well, all the solutions have modulus root 2, so they all lie on this circle with radius root 2. The first one had an argument pi by 20, which is quite small. So z0 lies about here. And that's the complex number in polar form, root 2 pi by 20. The next solution that Sarah found, z1, well, that had an argument pi by 4. So z1 will be here. And in polar form, that's root 2 pi by 4. But that was the 1 plus I in Cartesian form. And then each time you add on pi by 5 to get to the next solution. So adding pi by 5 to z1 gives us z2, and adding pi by 5 as an argument to z2 gives us z3, and continually adding the pi by 5s takes us right round. Now, if we were to continue beyond z9, we'd get back to z0. So you can see by this, these are equally spaced round the circle and stopping at z9 because z0 gets us back to where we started. So that's why Sarah stopped after 10 solutions. So the solutions, as I said, are regularly spaced round the circle. That's important. And that always happens when you solve equations of the form z to a power equals something.
So you can find the roots algebraically using polar form, but when you plot the roots on an Argand diagram, you'll see that they're regularly spaced around a circle. And that's a very useful geometric check that you've done the algebra correctly. And that's what Algebra Workout is all about. Goodbye.
Goodbye.